Welcome to The Explainer, where we're jumping right into the most powerful, cataclysmic, and honestly, awe-inspiring explosions in the entire universe. We're talking about supernovas. Today, we aren't just looking at how massive stars die. We're actually going to discover how literally everything around us, including you and me, came to be. So look at this number, 10 billion. At their absolute peak, these violent stellar deaths can outshine 10 billion suns. Think about that. For a brief moment, a single supernova can outshine the entire galaxy it sits in. But here is the truly staggering part. That blinding visible light, it represents less than a fraction of 1% of the total energy actually released in the explosion. The rest of it is completely invisible to our eyes. Here's our roadmap for today. First, the ultimate cosmic catastrophe. Second, anatomy of stellar death. Third, types of stellar explosions. Fourth, the cosmic elements forge. And finally, echoes across the universe.
Okay, Section 1, the ultimate cosmic catastrophe, grasping the scale of supernova. To really wrap our heads around the mind-bending scale we're dealing with here, let's look at this quote. In the first 10 seconds, as much energy radiates from a tiny core 30 kilometers across as from all of the other stars and galaxies in the entire visible universe. I mean, just pause and think about that. A single supernova releases an unthinkable amount of kinetic energy. We're talking about stellar material being violently ejected outwards at speeds up to 45 million miles per hour. It's an event of absolute, unadulterated cosmic violence. So you're probably wondering, how often does this actually happen in our cosmic neighborhood? Well, in the Milky Way, we average one supernova explosion every 25 to 100 years. They blast material out at roughly 10,000 kilometers per second, and they act as the primary source of high-energy cosmic rays in our galaxy. And this brilliantly illustrates a key point. While we love studying them from afar, they are incredibly dangerous. If a supernova were to detonate too close to Earth, that intense wash of radiation and high-energy particles could devastate our atmosphere and wipe out biological life. Luckily, there are no immediate candidates close enough to cause us any harm right now. Moving on to Section 2, Anatomy of Stellar Death, how massive stars run out of fuel. To truly understand that massive blast, we have to rewind a bit and look at the life of the star leading up to it. How does a massive star actually die? Well, it all comes down to a constant, epic battle between gravity pulling inward and nuclear fusion pushing outward. Throughout its life, a massive star fuses progressively heavier elements in its core, hydrogen to helium, carbon, neon, oxygen, and silicon. But then it hits a wall. Iron. Fusing iron doesn't release energy, it absorbs it. These endothermic reactions completely stall the star's fusion engine. Suddenly, that outward pressure just vanishes, and gravity wins. In a fraction of a second, the core buckles under its own immense weight, falling inward at a quarter of the speed of light before bouncing off its ultra-dense center to create a colossal outward shockwave. But here's the crazy twist. That rebounding shockwave, it actually stalls out on its way to the surface of the star. It basically gets bogged down. So what revives it? Neutrinos. Remember earlier when I said visible light is less than 1% of the explosion? Well, it's these elusive, weakly interacting neutrinos that carry away roughly 99% of the dying star's gravitational energy. As trillions of them escape the collapsing core, they deposit just enough intense heat behind the stalled shockwave to push it outward and physically drive the star to explode. It's like a cosmic kickstart. Section 3. Types of stellar explosions. Classifying the cosmos's biggest blasts. Now, not all stars die the exact same way, and astronomers kind of act like cosmic detectives to figure out what just blew up. They classify these blasts into two main categories, Type 1 and Type 2. Type 1 is a thermonuclear explosion. This happens in a binary system when a dense, dead star called a white dwarf steals too much matter from its companion star, reaches a critical mass limit, and completely obliterates itself. Literally leaves nothing behind. On the flip side, Type 2 is the core collapse explosion we just talked about. It happens to massive stars. We're talking over 8 times the mass of our sun. And rather than completely destroying the star, the crushed core actually remains behind, forming either a hyper-dense neutron star or, if it's massive enough, a black hole. This brilliant taxonomy visually maps out the spectral fingerprints astronomers look for as clues. When a star explodes, scientists analyze the light it emits, which is its spectrum. If they see strong hydrogen features, bingo, they know it's a type 2 core collapse. If there's no hydrogen but they see ionized silicon, they know they're looking at a type A white dwarf explosion. It's an incredibly precise way to classify the violent deaths of stars that are billions of light years away. But, the universe always has some surprises up its sleeve. For decades, scientists theorized about a rare, borderline explosion that bridges the gap between these two major types. They called it the electron capture supernova. This happens in intermediate stars right on the borderline, around 8 to 10 solar masses. Instead of an iron core, they develop a core of oxygen, neon, and magnesium. Before they can ever even fuse iron, gravity becomes so intense, it literally smashes electrons directly into atomic nuclei. The core loses its pressure support and just prematurely buckles. And the amazing part? We finally confirmed this theory recently with the observation of supernova 2018 XD.
All right, Section 4, the cosmic elements forge, where the building blocks of life are made.
So why does all this stellar death actually matter to us here on Earth? Well, because these explosions are the very forges of creation. During a star's normal life, it fuses lighter elements up to iron, but the universe is full of elements heavier than iron, right? Think of gold, uranium, iodine. Where do they come from? They require the extreme, sudden heating of the explosive shockwave and a mechanism called the R process, which stands for rapid neutron capture. In the absolute chaos of the explosion, atomic nuclei are bombarded with neutrons so rapidly that they build up into the heaviest elements on the periodic table before they even have a chance to decay.
So the absolutely crucial point to take away from this explainer is this. Without these explosive deaths, planets like Earth just wouldn't exist. The calcium in your bones, the oxygen you breathe, and the iron in your blood were literally forged in the fiery deaths of ancient massive stars. Every single time a supernova explodes, it enriches the interstellar clouds with these heavy elements, seeding the next generation of star systems with the very building blocks necessary for biological life.
Section 5. Echoes across the universe, observing historical remnants and distant galaxies. Now, we've actually been watching these cosmic forges from Earth for thousands of years. We have an incredible historical record of these events. Back in 185 AD, ancient astronomers recorded a guest star that we now know is the remnant RCW 86. In 1054 AD, observers around the entire world documented a brilliant light that we've since identified as the explosion that created the famous Crab Nebula. And then, of course, we have Tycho's and Kepler's supernovas in the 1500s and 1600s. Fast forward to 1987, and modern astronomers got a front-row seat to SN 1987A in a neighboring galaxy. That event was huge because it actually allowed us to physically detect the burst of neutrinos we talked about earlier.
Today, our view goes so much further. Just take a look at supernova 2014J. It's a Type I thermonuclear explosion located in the Cigar Galaxy, approximately 11.5 million light-years away from Earth. Because of modern telescopes like Hubble, we can spot these cosmic detonations across vast intergalactic distances, literally identifying them outshining the centers of their entire host galaxies.
And being able to see them from so far away is incredibly useful for us, especially those Type A explosions. Because Type A supernovas always occur when a white dwarf hits that highly specific critical mass limit called the Chandrasekhar limit. They act as standard candles. This means they all explode with a very uniform, predictable peak brightness. By measuring exactly how bright they appear to us from Earth, scientists can calculate exactly how far away they are. In fact, observing these standard candles is exactly how astronomers originally discovered that the expansion of our universe is accelerating, driven by mysterious dark energy. We're continually pushing the boundaries of what these explosions can teach us. Just look at the recently discovered SN Winnie. This is a rare superluminous supernova roughly 10 billion light-years away. But here's the really wild part. Because the gravity of galaxies sitting between us and the explosion physically bends the light, a process called gravitational lensing, SN Winnie actually appears 5 separate times in our sky. Because the light takes slightly different paths around the foreground galaxies, those 5 images arrive at slightly different times. By measuring those specific delays, scientists are actually calculating the true expansion rate of the universe. Which all leads us to a truly profound thought to end on today. We've seen how the catastrophic collapse of massive stars creates the very atoms required for biology and planets. We've seen how the thermonuclear destruction of white dwarfs acts as a cosmic measuring tape, revealing the hidden influence of dark energy. So my question to you is this. If the death of stars drives both the creation of life and our mapping of the expanding cosmos, what will these magnificent standard candles ultimately reveal about the final destiny of our universe? Thank you so much for joining me on this explainer. Keep looking up and keep asking questions.